we have vector field. Now all of us we are going to discuss about vector field and scalar field. Look, from what you will have to understand little bit, but yes, at least little bit. Field means field, reason, yeah, area. So field of vector, okay, field of vector is vector field. We will explore more about vector field, don't worry. A scalar field means field of a scalar quantities, field of a scalar quantity. Vector field means field of vector quantities, okay, vector quantity. PPT explains about it as field of a physical quantity. Since we know that we have vector quantities a scalar quantity, so field of a scalar quantities is a scalar field, field of vector quantities is vector field, okay. So field of a physical quantity can be expressed as a continuous function. Continuous function means equal distance between 2 points, initial and final. And again this point come, 2 points are coming again, so our length is the same. This is what is meaning of a continuous function, okay. Expressed as a continuous function of a position of a point in the region of a space. There is a space, let's just say this is a space, and we can also say a space means this is an empty area, okay, and this is area, or you can say region, a space. This point, let's just say all these are quantities which are scalar quantities. Of course you will get magnitude only. If all these are vector quantities, what things will you get? You will get magnitude with velocity, with direction, okay. This function is called, this one point is called point function. This one point we will call it as a point function, okay. Point function. This one point is nothing but it can be a scalar quantity or vector quantity. Point function and the region in which it is specified is known as field. We know this is present in this region. So if this region is vector, we will say yes, this point function is present in vector field. If this space is a scalar field, then you can say this point function is present in a scalar field. That is how you will understand. So we are starting with the vector field. Again, I will read PPT. When a vector physical quantity, try to understand. When a vector physical quantity is expressed from this point, if a vector quantities is being expressed, or you can say is being explained or discussed from this point, we are talking about a physical quantity from point to point in a region of a space by a continuous vector function. Let's suppose over here vector is what? This is vector and coordinates are x, y, z. These are coordinates. Remember, it is a function. Function means we put a value of a variable, then we get output. We put input and we get output. This is what is meaning of a function. So x, y, z. Here we will put value of x. So continuous, it is changing. Yeah, this is variable. This is a variable. It is changing. So then the reason is a vector field. Yeah, reason is a vector field, and the function This a vector is known as a vector point function. Remember, this will be our vector point function. Vector point function. Try to understand. It will perform as a function. This as a point. According to this point, we are talking about a vector which is a vector, and this is a present in a space which is nothing but vector field. How vector field? This arrow. From arrow we are saying this is vector field. Okay. So I hope you understood what is this. So this is nothing but vector point function. This is vector point function. Next we have a scalar field. We need a scalar physical quantity. A scalar physical quantity. When a scalar physical quantity is expressed from point to point in a region, from this point to this point, from this point to this point, in a region of a space by continuous point, this is continuous point. Okay, from this point to this point, this point to this point, that is how we are expressing a physical quantity, which is a scalar quantity. So the function will be nothing but, we will take what function? We will take the, let's suppose this is a points. Okay, this is point which is a continuous. So this will be our phi. Phi will tell us that yes, we have a point which is representing a scalar field. Okay, so this will be our phi, and coordinates of this will be x, y, z. Try to understand. If there is a vector, we will understand yes, this is a percent. It is a vector point function which is a percent in vector field. But Fission is providing this phi, then you will understand that yes, it is there is a point, or there is a quantity, magnitude, which is a present in a scalar field. From the phi you will understand. Okay? From the phi, a scalar physical quantity. Got it? So we will have coordinates of phi as well as coordinates of a vector. This xyz will tell you location of a quantity, location of a magnitude, location of a direction. Okay? I hope you understand. So then the reason is a scalar field. If a phi is coming, then we will say yes, reason is a scalar field. The function phi is known as a scalar point function. This phi is working as a function, remember, and this vector a is working as a function. That's why at this point this will be vector point function, because it is a vector, and at this point this is present and this is working as a function. Now what about this? This phi is a present at this point, so this will be our a scalar point function. This will be a scalar point function. A scalar point function. Okay. Phi is a scalar. Phi is a present at point, and it is working as a function. I hope you are understanding. Function means at each point its value will change. Yeah, its value will change at each point. And vector point function means at each point value of a vector will change and direction will change. This is what is meaning of a vector point function. And meaning of this phi x, z, y, z means at each point value will change, which is meaning of a scalar point function. a scalar point function. Okay, this is enough about vector field and a scalar field. About vector field and a scalar field. Now, after this, we understand a gradient about the gradient, divergence, curl. In details, we are going to explore it. So gradient, let's explore gradient. Remember, whenever this phi is coming, just understand this is nothing but a scalar point function, which is at a point in a scalar field. That is what you understand it. Okay. Now gradient. Gradient. If phi is a scalar function of a position, try to understand. If phi is a scalar function of a position in a space x, y, z, then its partial derivatives along the three orthogonal axes are. Try to understand. If a phi is a scalar function, we are crystal clear about phi. Phi is a scalar function which is present in a scalar function. That's why it is a scalar function. If a phi is a scalar function of a position point in a space x, y, z. X, y, z is nothing but this is providing a space in 3 dimensions. In 3 dimensions, there is a location of a point which is nothing but phi is a scalar function. Then it's a partial derivatives. Along the partial derivatives means this d upon dx. Okay. Partial derivatives along the 3 orthogonal axes. 3 orthogonal axes means I cap, j cap, k cap, and coordinates will be x, y, z. Okay, x, y, z. So it's a partial derivative. This is a partial derivative. Along x axis, first of all x axis, then y axis. Okay, so x, and x axis provides I cap. But this is a what? It is a scalar function. So phi comma d phi upon dx dy d phi upon dz. These 3 things we will get when phi is a scalar function. Then derivatives of 3 orthogonal axes, or you can say 3 axes, will be phi upon phi d phi upon dx plus d phi upon dy plus d phi upon dz. Okay, this is nothing but partial derivatives. Partial derivatives along 3 axes. 3 axes. Okay. Then gradient of phi. Try to understand. Gradient of phi Gradient is nothing but, I think it should be partial derivatives or del operator. This d upon dx is nothing but del operator. So when we use a del operator, so we write this three axis with addition. D upon dx plus d upon dy plus d upon dz, that is how it. So gradient is nothing but del operator. Okay, so gradient is nothing but del operator. Del operator. So you can write this d upon dx, d upon dx. Okay. I cap plus dy z cap plus d upon dz k cap n2, or you can say dot 5. Just multiply this by this term, this by this term, this by this term, then you will see that it is becoming nothing but d phi upon d x I cap plus d phi upon d y plus d, but over here this will be z cap, d phi upon d z k cap. This thing we will get after multiplying this phi by this thing. Okay, by this thing. So finally we can say this is our equation number 1. This is the equation number 1. So gradient of this phi is nothing but del operator of phi. Del operator of phi. Okay. In vector algebra, an operator known as del or nabla. Okay. Remember, in vector algebra, this an operator now as this a del vector, which is nothing but it is a del or nabla. We will talk about Laplacian operator. Right now, just understand del operator is nothing but this. Just remove this phi, then you will get del operator. But you will have to add positive sign with x z x with I z k cap. Clear? So you can say this is nothing but it is equal to I upon d upon dx I cap plus d upon dy z cap plus d upon dz k cap. Got it? Got it. This is our complete del operator, and we used this del operator with a phi, and it played a important role with the gradient. Played as an important role to define gradient. This del operator is a gradient. Okay, it's not different for gradient. Clear? Now over here we can write this over here. Del operator dot phi. It will be equal to, just put this over here and multiply this by phi. So d upon dx I cap plus d upon dy j cap plus d upon dz, and multiply this by 5. Okay, by 5 you will get d phi upon dx I cap plus d phi upon dy j cap plus d phi upon dz k cap. This is our second equation. You can see both are same. Both are same. First equation is equal to second equation. You can see first equation is equal to second equation. That's why I was saying that gradient is nothing but this is a del operator. I will be as it. So finally you can say finally or hence gradient of phi is equal to del operator of phi, or you would say, remember this is dot product, okay? So grad of phi is equal to del operator dot phi. Both are equal. Okay. Last sentence. The del operator is a vector operator, but it is not. Remember, this del operator is vector operator, but not a vector quantity. We use this del vector with quantity so that we can get a scalar quantity or vector quantity. Okay. So this del vector, remember, this is a del vector, not a del vector quantity. Clear? This is a del operator vector, you can say. Vector operator. When operated with a scalar, it converts a scalar physical quantity to vector physical quantity. It is known as a gradient of the scalar point function phi. When you will use this del operator with a scalar quantity, then it will convert into vector. It will convert a physical quantity, which was phi, to vector physical quantity. Okay. So del operator into phi will give us a vector quantity. But all the times this will not happen, where you are using del operator with just you are multiplying a physical a scalar quantity by del operator, then you think, yeah, okay, at the end I will get a vector quantity. Yeah, it can happen. It will be possible that you will get a vector quantity when you are multiplying, you are using del operator with a scalar quantity. Then yes, there will be a 75% chance to get a vector quantity as a result. And when you are using what a vector quantity, you are using a del operator, or you can say you are multiplying del operator by a vector quantity, then what will happen? I think a scalar quantity you will get. You might get a scalar quantity. Okay. Just we use this del operator with a scalar quantity or physical vector quantity, so that we can get result as a scalar quantity or physical quantity. But this del operator is not a vector quantity. It is only vector, or you can say vector operator. Clear? Vector operator. Now we are going to take question based on this derivation. based on this derivation. Let's see what did we do. We wrote only, we wrote that phi is a scalar function. If phi is a scalar function of a position in a space x, y, z, then of course it's a partial derivatives along the three orthogonal axis will be what? First axis we will take, which will be x, second y, third z. So since we have partial derivatives, so partial derivatives is nothing but d upon dx, d upon dy. This is partial derivatives, and just we multiplied phi, okay. So then gradient of phi will be equal to, and we know that gradient is nothing but this is a del operator. So del operator we used over here with position, or you can say with direction, like I take it, and then into phi. Then we simplified it, we got this, and we assumed, or you can say we put it as a equation number 1. Then we thought that in vector algebra an operator known as a del operator is nothing. This name of this del operator is also nebula. Okay, nebula. So this is equal to, del operator is equal to this much partial derivatives along x, partial derivatives along y. Add. This is nothing but del operator. Then we multiplied this del operator by phi. Same thing we got, and we put it as a second equation. We observe that equation number 1 is equal to equation number 2. So finally, we found the conclusion. Gradient of phi came out as equal to the del operator into phi. So from this we understood completely that gradient is equal to del operator. Gradient is equal to del operator. Okay. Now next question. Question based on this concept, or you can say on this gradient, or on this derivation. Question number 1. If phi x comma y comma z, can you tell me what is it? Can you tell me? Could you tell me what is it? Phi x y z. X y z is a space of scalar quantities. So phi is nothing but this is a scalar point function. Okay, phi is nothing but a scalar point function, which is equal to location of this point function, a scalar point function, is given, which is 3x square y minus y raised to power 3 z square. Then we have to find the value of grad phi dot phi at 1 comma minus 2 comma minus 1. Okay, look at this point you have to find grad of phi, where, remember, these are coordinates. Okay, these are coordinates, and this is nothing. I think it should be position vector, I think so. If no, then okay, no problem. This is nothing but it is a scalar point function. This is a scalar point function, and this is point. At this point This is a scalar point function. We have to find grad phi. Okay, grad phi. Grad phi. So what will we do? First of all, we are going to find grad phi at this point. Phi is given. Phi is given. First of all, let me tell that yes, that is how you will solve this question. At this point, we have to find grad phi. Then phi is given. Grad we now it is nothing but grad phi is equal to tail operator dot phi. Value of tail operator we know. Yeah. Then just multiple by phi whose values are given. Then you will use your dot product, and that is how your answer will come. That is how your answer will come. Okay, so let's solve it. Let's solve. Look at over. Grad phi at a point of 1 comma minus 2 comma minus 1. Okay, phi is given 3x square y minus y cube z square. Got it. Got it. You know that grad phi is equal to del operator dot phi. Okay. No problem. Del here, no problem. Now we will just substitute value of del operator and value of phi which is given over here. So this will be equal to d upon dx I cap plus d upon dy j cap plus d upon dz k cap dot phi. Values of phi are 3x square y minus y cube z square. Okay, just substitute value this in first term, this in second term, this in third term. Okay, third term. This will be your 3x square y minus y cube z square I cap plus 3x square y minus y cube z square upon dy d upon dy 3x square y minus y cube z square. Now we have partial derivation. First of all, we will differentiate this with respect to x and this with respect to x. You can see differentiation, partial differentiation of this with respect to this will become 0. Reason is there is no x in this, and we are differentiating this with respect to dx. That's all. So yes, this will not be equal to 0. Y will come out as a outsider. So differentiation of x square will be 3 to the 6x. Are you understanding? Are we correct? Yeah, we are correct. So look at over here. This will become 6xy. Am I correct? And this will differentiation of this by dx will become 0. Reason is there is no x in numerator. Okay, xi cap. Okay, then plus. Here we have y in the numerator, but in numerator we have also y. So that's why it will not be equal to 0. Okay, so 3x square will be as it. A differentiation of a y will become 1. I think 1. 3x square minus, here you can see y raised to power 3 z raised to power 3 upon dy is not equal to 0. The reason is in numerator we have y and also in denominator we have y. That's it. So z square will be as it, okay? So 3y raised to power 2 z square. Clear? Z cap plus here same over here 3x square minus 3y square z square. But hold on. Here it should be z. So this will become 0 and we have this thing which is a minus. So this will become minus y cube 2z k cap 2z k cap. Okay. Just substitute value of x, value of y and value of z. As you know, question provided these values. So these values x, y, z. 6 multiple x is how much? 1. Y is how much? -2. I cap plus 3 multiple x is 1 raised to power 2 minus 3 multiple y is -2 raised to power 2. My multiplication z -1 raised to power 2. Okay, z cap minus y is -2 raised to power 3. Then 2 multiple z is -1. Okay. Okay. Now let's simplify it. 6 to the 12 minus 12 I cap plus 3 3 minus 2 to the 4 3 is 12 3 minus 12 9 minus 9 z cap. Then we have minus 8 8 to the 16 minus 16 minus 1 minus 70 minus 20 plus 20 k cap. Is this answer correct? Yes, this is correct, but it should be 16. It should be 16 k cap. Look at this part. Look at this answer. How did a minus 16 come? How did a minus 16 come? Minus as it. This will be minus it. Minus 16. Then we have minus 1. This minus will become positive. So this is giving us plus positive. But hold on. This is positive. So minus 16 and minus 1 will be minus 70. Will be what? Minus 70. Minus 2 raised to power 3 minus 1. Minus 2 multiple 8 minus 1 minus 16 minus 1. So yes, this should be positive. Plus 15. Plus 15. This should be plus 15k. This minus over here. Look at over here. Minus as it. Minus as it. Okay. Value of y is minus 2 raised to power 3 multiple 2 multiple value of z is minus 1 minus 1. Okay, so minus, and this will be minus 8 minus multiple minus 2, 8 to the 16 minus 16k. Yes, over here we will have minus 16k. This is our final answer. Remember, it is nothing but grad of a phi is equal to del operator of a phi is equal to minus 12 I 12 minus 12 I cap minus 9 z cap minus 16 k cap. This is our final answer. This is our final answer. This is our final answer. Now next question. Now let's take next question as a practice. As a practice, if phi x comma y comma z is equal to 6x square y plus 2y square z plus 2x square zy, then find the value of gradient phi at 2 comma minus 2 comma minus 3. Okay, look at value of a scalar point function is given, coordinates are also given as a number, and as it is asking only gradient of a phi. Phi comes and dot is coming, dot is coming. So you can say that phi is equal to 6x square y plus 2y square z plus 2x square zy. Gradient phi at 2 comma minus 2 comma minus 3. Okay, minus 3. Hence x is a 2, y is a minus 2, and z is a minus 3. Z is a minus 3. Got it? You know that this grad phi is equal to del operator phi. Okay, and this is equal to d phi dx I cap plus d upon dy j cap plus d upon dz k cap. And value of phi is how much? 6x square y plus 2y square z plus 2x square zy. Okay, this is value of phi, and we are using dot product. We are using dot product because of phi is given. If there is a vector, then we use divergence of a vector. Okay, divergence of vector. Okay, so just multiple what? Just keep this in first term, this in second term, this in third term. Okay, third term. D upon dx 6x square y plus 2y square z plus 2x square zy I cap. Okay, no problem. Partial derivatives of 6x square y plus 2y square z plus 2x square zy. Okay, no problem. Z cap plus d upon dz 6x square y plus 2y square z plus 2x square zy k cap. Okay, till here we are crystal clear. There is a no dot till here, yeah. All dots are crystal clear. Now let's differentiate each terms. Look at over here. We can differentiate this. This upon this is not equal to 0. So 6 to 12 x y. This will become 12 xy plus this upon this will become 0. This upon this. So 2 to the 4x zy 2x square. Partial derivatives of 2x square zy upon dx is nothing but 4x zy. 2 to the 4. Yeah. It is along I cap. It is along I cap. Got it? Got it? Now over here, this will become x square. X square plus 2 to the 4yz plus 2x square z. Am I correct? Yeah. Each terms in this bracket came out as a differentiate, not a 0, not equal to 0, but something. Then plus this derivative, partial derivatives of this with respect to dz. So this will become 0. And over here 2y square, okay, plus 2x square y k cap. Now our work is to substitute value. So phi at 2 comma minus 2 minus 3 means x is 2, y is minus 2, and z is minus 3. All this value we have to put in this equation so that we can get final answer as a gradient of phi, gradient dot phi, not 5. So 12 multiple 2 multiple minus 2, hold on. 2 plus 4 multiple 2 4 multiple 2 multiple minus 3 minus 3 minus 3 and value of y is minus 2. Till here it is crystal clear. I cap plus I cap plus. Okay, no problem. This is a 2 raised to power 2. We cancel 4 plus 4 multiple minus 2 multiple minus 3 plus 2 multiple 2 raised to 2 4, it will become 4 multiple z minus 3. Okay, this is along z cap plus 2 multiple minus 2 raised to power 2 plus 2 multiple 2 raised to power 2 multiple y which is minus 2 along k cap okay. Got it. Are you crystal clear about? Is this clear? Till here? Now just to simplify this for next step. 12 twos are 24. 24 twos are 48. 48 minus 48 plus 4 twos are 8. 8 6 are 48. 4 twos are 8. 8 3s are 24. 24 twos are 48. So minus minus will become positive. So 48. Answer is 48. Okay, I cap plus 4 and then plus. So 4 plus 4 plus 4 2s are 8, 8 3s are 24. 24, okay. This is along Z cap plus. Hold on. And it is a 28. This is a 28. This is a 28 plus 4 2s are 8 and 8 3s are 24, which is a minus 24. Minus 24. Z cap plus this is along Z cap. 2 multiple 2 to the 4, 4 to the 8. 4 to the 8 plus 4 to the 8 plus 2 to the 4, 4 to the 8, 8 to the 16, minus 16. Minus 16 along K cap. Okay, no problem. This will become 0. You can say 0 I cap. 0 I cap plus 24, not a 24 but 4 Z cap plus 4 Z cap minus 8 K cap. This is our final answer. It can be written as 4Z minus 8K, where this is 0. This is our final answer, and you can say grad dot phi is equal to del operator phi is equal to 4Z minus 8K. This is our answer. Check it. Is my answer correct? Yes, answer is correct. Plus 4Z and minus 8K. Answer is correct. Answer is correct. You can see. It looks large. It looks big, but once you understand carefully, it becomes easy. It becomes very easy, very easy. Okay, now next question. Next question. If R vector is the position vector of a point, find the grad dot R. Grad dot R. This is the question. Let's solve. Let's solve. R vector is the position vector. If R vector is the position vector, so you know value of a grad you know, but value of R is what? So you know position vector is nothing but Rx. This is written as x I cap plus y j cap plus k cap z k cap. Okay. Here magnitude of position vector is what? Magnitude of a position vector is nothing but x square plus y square plus z square. This is a magnitude of R, where we remove I, j, k cap because we used mod. Okay, so magnitude of position vector will be equal to under root of x square plus y square plus z square. Now we have value of R, we have value of gradient. It's enough to solve it. It's enough, completely enough. Completely enough. So let's solve. Grad dot R will be equal to del operator dot R. Just in place of phi we have R. In place of phi we have R. Okay. So this will be equal to d upon dx I cap plus d upon dy j cap plus d upon dz k cap dot with R. So value of R is this much. You can write this as x square plus y square plus z square raised to power 1 upon 2. Am I correct? Am I correct? So value of root is nothing but 1 upon 2. 1 upon 2. So just substitute value over here. X square plus y square plus z square, which is 1 upon 2. And put this with this first term, this with the second term, this with the third term. Okay? Am I correct? Let's do it. So d upon dx, we have x square plus y square plus z square raised to power 1 upon 2. 1 upon 2. Got it. I cap plus d upon dx, x square plus y square plus z square 1 upon 2. 1 upon 2, it is along with the j cap plus d upon d, but hold on, this is a dy and dz, x square plus y square plus z square 1 upon 2. 1 upon 2. Okay, till here this is crystal clear. There is no doubt, I think so. I think so. You don't have any dot till here. Just we put this value with each term. Okay. Now we will use a partial depreciation. Partial depreciation. So if you see, complete depreciation of this will be what? 1 upon 2. So 1 upon 2 will come over here. Can you write x square plus y square plus z square? So depreciation of this will be what? 1 upon 2 x square plus y square plus z square. Am I correct? But here we will have to use minus 1. Okay, minus 1. Minus 1. So it becomes minus 1 by 2. This minus 1 by 2. This minus 1 by 2. n x raised to power minus n. n x raised to power minus n. Clear? Okay. So you know that y dy square with respect to dx it will become 0. Dz square with respect to dx it will become 0. You know. Okay. So finally, you can write this as a one by 2 x square plus y square plus z square. Then partial depreciation of x square with respect to dx will be 2x. Am I correct? Along I cap. Okay, along I cap. But over here, this will be minus 1 upon 2. Minus 1 upon 2. Okay, minus 1 upon 2. This 2 will cut to each other. Now look at over here. 1 upon 2 x square plus y square plus z square upon minus 1 upon 2, and the partial depreciation of a y square will be 2y, and this 2 will cut to each other. Got it? This is along z cap. Then 1 upon 2, this is downward, this is over here down, and x square plus y square plus z square minus 1 upon 2, and partial depreciation of z square with respect to dz will be 2z, and this 2 will cut to each other. So finally we have x square plus y square plus z square raised to power minus 1 upon 2 I cap plus x square plus y square plus z square raised to power minus 1 upon 2. But hold on, here we have x and here we have y. This is along z cap plus x square plus y square plus z square raised to power minus 1 upon 2 into z. This thing we got. Tell me what thing you are getting as a common. You are getting as a common. What thing? So answer is this is common. X square plus y square plus z square raised to power minus 1 upon 2 is the common for each term. So you can take this as a common. So x square plus y square plus z square raised to power minus 1 upon 2. Not x, okay, not x. So finally we will have x I cap plus y z cap plus z k cap. And here you can see this is the value of r vector. This is the value of r vector. Am I correct? R vector. Look at, and x square plus y square plus z square. This is a value of r square. This is a value of, or you can say x square plus y square plus z square raised to power minus 1 upon 2. Don't think about minus, just think about it. So this will be r square raised to power minus 1 upon 2 dot, this is the value of position vector, which is r vector. Just bring this in denominator. What will happen? R2 upon, this can be written so finally answer will be grad of r is equal to r upon r vector upon r. Can you write this r2 upon this r2 can be written as r2, look at it, minus 1 upon 2. Here you know that this is nothing but it is value of root. So this minus r square, this square will cut this root. So finally we have minus r, and minus r, it is nothing but 1 upon r, and this r can be written as minus 1, yeah, minus 1. So finally we have 1 upon r, and this r vector, which is the denominator. This is our answer.